let's look at a little bit more complicated function. We have e to the x over 1 plus e to the 2x. Notice that the bottom is never 0. E to the 2x is always positive, and then we add 1, so we're getting something always bigger than 1. So this doesn't have any vertical asymptotes. I'm not worried about the function being unbounded. I am worried about the integral being unbounded. In fact, it does it on both ends. So we're going to split this into 2 pieces because we never want to have one integral with more than one infinity showing up. It's too hard to deal with. So you pick any number between negative infinity and infinity to split this in half at. I'm going to go ahead and pick 0, but you absolutely don't have to. You can pick whatever you want. And we're going to split our integral into 2. And then we can go ahead and we can introduce our limits. So I'm going to replace negative infinity with, I don't know, n. And I'm going to replace positive infinity with an m. Again, the idea is we can't just do f of infinity, big F of infinity minus big F of 0. But we can do big F of a variable and let the variable get infinitely large. So we're sneaking up on infinity. Okay, so antiderivative. This is where this one's a little bit interesting, and I'm going to actually go off and do some side work because I really don't like having to write the limit over and over and over again for both of those. E to the 2x. To find the antiderivative, I'm going to need a substitution on this one. So I'm going to let u equal 1 plus e to the, what do I want to do here? Let me think about this for just a second. E to the x, e to the x. Nope, I changed my mind. I want to think about this as, that's actually slightly tricky, e to the x squared, and I'm going to let my u be an e to the x. We'll see if this works for me. I think it will, which means my du will be the same as e to the x dx, which is nice because I have that. So this is going to turn into a du over 1 plus u squared. Which I know, if I'm not forgetting, is arctan. So this is arctan of u, and we need to switch back, so it's arctan of e to the x c. We will need the plus c over here, so we'll just say, okay, we have the limit as n approaches negative infinity of arctan of e to the x, evaluated from n to 0, limit as m goes to infinity of arctan e to the x from 0 to m. Okay, so this is the thing. They get a little tedious on the writing sometimes, especially when you have to split them up. But I don't think you have a ton that you have to do into 2. We're going to get arctan of e to the 0. E to the 0 is 1, so we have arctan of 1 minus arctan of n, and then we'll have a plus limit as m goes to positive infinity of arctan of, what am I doing? Oh, I'm messing things up. This is e to the n, not n. And then arctan of e to the m minus arctan, whoa, that was craziness, of e to the 0, which is 1. Arctan of 1, that's asking what angle or arc length will give you tangent or slope of 1, and that's going to be a pi over 4. So you can sneak that in here if you want as well. But I'm also noticing that the limit doesn't really affect arctan, not really, it doesn't affect arctan at all, so you can actually separate that out. You can say, okay, well, the limit as n goes to negative infinity of pi over 4 is just pi over 4. So we'll go ahead and write it, but they are going to end up canceling themselves out. Arctan of e to the n. Okay, so as n goes to negative infinity, e to the n is getting really close to 0, right? So if we're raising e to really big negative powers, that's going to give us a tiny, tiny, tiny number. And arctan of 0, we're asking what angle gives a slope of 0. That's going to be 0. So this whole thing is going to 0. So that's not really very exciting, but we'll write it down. And then this one, as m gets really, really big, is going to infinity. Arctan, if we're looking, I don't know how you want to see this. If we're looking in the picture, if we're looking for the angle that'll give us an infinite slope, to get closer and closer to that infinite slope, you're going to have to get closer and closer to pi over 2. You could also think about that one if you remember the graph of arctan, if this is easier for you. It has asymptotes at pi over 2 and at negative pi over 2. So we're just going to be approaching that pi over 2. And then we already decided that arctan of 1 is a pi over 4. So the pi over 4s are going to knock themselves out. The 0 is not interesting at all to me. It turns out that this curve, and it might be fun to go look at a graph of it, is going to capture an area of pi over 2, even though we're going all the way from negative infinity to infinity. So I don't know perfectly what this looks like, but you should see something like this happening. Would it have its max at 0? Something along those lines anyway. So this one, wherever the hump is, the tails are so flat that that actually is a finite amount of area, which is crazy, but that's what this is telling us. Crazy but true. Okay, thanks for watching.